Hello everyone and welcome to Digital Elevation Models and Application course. And in the today's topic, which is the 14th topic of this course, in today's topic we will be discussing about a few more derivatives of digital elevation models which we can drive. So first one is that topographic roughness, which is very important, and also it is called topographic positional index. So that can be used for determine the ruggedness of a terrain, because otherwise everything becomes subjective, and through visual interpretations we may say that the terrain is smooth or rugged, but can we bring some quantities to it, can we bring some index to it or indices to it, and that is the approach here. So we will be putting our digital elevation models and for this analysis, which is basically relative topographic position, or also called topographic position index. And of course the input is always here as usual is digital elevation model. So topographic roughness, if we define, that is ruggedness is defined differently depending on the calculation used, and mainly the main point would be here is the scale at which we will be determining the topographic positioning index. So TPI will depend on scale that we will also discuss in detail. So how basically it is depends the fundamentally behind this topographic position index is the slope, and so how much it is deviating from a sloping surface, that is standard deviation of slope, and which may be based on our TPI or ruggedness roughness may be based on standard deviation of elevations, how elevations are changing. So slope and elevation, they are interlinked in here. Then slope convexity, whether slopes are convex, concave, that too we have also discussed, and down slope or across slope, these parameters we have discussed in previous discussion. And fourth in this may be based on the variability of plan convexity, that is contour curvature, or some other measure of topographic texture. So these will determine our topographic roughness or TPI. And so scale, as I have mentioned earlier, that scale is important in any roughness analysis, both at the DM, at the landscape features you intend to characterize. So here the scale, that is the resolution of digital elevation model, will also play a very important role. And secondly, at what scale we are analyzing this situation. So we will see how the scale affects the TPI or topographic positioning index. In many cases, the starting a smooth DM produces a more interpretable roughness raster, and then there are several ways to calculate topographic roughness. One, the most popular one, which we will also see here, that how we can calculate TPI. So topographic position of each pixel is identified with respect to its local neighborhood, and that is why it is in the beginning it is said the relative topographic position roughness. So that is because the calculation is basically based on the neighboring pixels, what is their elevation, and of course the slope is determined based on that also. So the index is useful, this TPI, for identifying landscape patterns, how landscape is there, what are the different landforms features which are present in a particular terrain or in a digital elevation model which has been subjected to TPI analysis, boundaries that may correspond with rock type, dominant geographic processes, soil characteristics, vegetation or air drainage. All these things can be used or can be identified based on this topographic positioning index. And the final, we can classify the output, and we can create on output in sense of high, medium or low based on natural breaks. So natural breaks like fault lines or some drainage lines or some geological features can also be incorporated, and index is also applicable to mathematic data. That means the data below the mean sea level underwater data. If that digital elevation model is available, then the same topographic index which can work for above mean sea level data can also work for below mean sea level data. So this TPI, topographic position index, at different scales and at different slope can be classified, or based on that DM can be classified. For example, slope position, sometimes we say this is ridge top, valley bottom or mid slope, etc. So when we emphasize on slope, where the slopes are positioned, then we can classify our digital elevation model based on ridge top, valley bottom and mid slope, etc. When we bring the landform category, then we can classify as a steep narrow canyons and gentle valleys, plains, open slopes, mesas, etc. And this way, as earlier I have mentioned that there are various ways of calculating topographic position index. We will take one of the very popular example given by Janus to calculate this one. So TPI basically is the basis of the classification system of landforms and is simply the difference between a cell elevation value and average elevation of neighborhood around that cell. So always for this calculation, the neighboring cells values or elevation values are considered, and degree to which it is higher or lower, thus the slope of the cell can be used to classify the cell into slope positions. And these positive values means the cell is higher than its surroundings, and vice versa, when while negative value will mean it is lower from surroundings. And if it is significantly higher than the surrounding neighborhood, then it is likely to be near or at the top of a hill or a ridge. So based on this, if it is too high, based on that we can say we can classify a landform as a hilltop or a ridge. Significantly low values suggest if TPI values we are getting very low value, then probably we are at the near the bottom of a valley. So this is how the interpretation of a TPI map can be done. And TPI values near zero could mean either a flat area or a mid slope areas are present there. And cell slopes can be used to distinguish the two, whether it is flat or not. Here is the example is given here that what we are having in zero values in the center. So the flat areas, if slope is shallow, or mid slope areas if significant slopes are there, then if we take towards the positive, then trends towards ridge tops and hilltops when we are having positive TPI values, very high, significantly high TPI value, that means we are definitely on the ridge or hilltop. Whereas significantly low and TPI value, that means it's a valley bottom, canyon, or in the maybe in the middle range also. So accordingly, based on these TPI values, we classify different landforms. So TPI, as have mentioned, that is a naturally it varies on the scale. Basically, it's a scale dependent, and because different neighborhood, and the example here through this schematic is that when if we get the TPI near zero, then we are basically on the hilltop. But if TPI is greater than zero, however the scale has changed, this is nothing but the scale var, and so this is a very large scale, and therefore your scale var is very small here. And if the TPI is equal to near about 0, then we are on the hilltop, but TPI is little greater than 0 when however the scale has changed, so we are not really on the hilltop. Now we are in the valley bottom. So it has given a completely different interpretation as scale has changed. If scale is further changed here, like here it becomes further smaller scale bar becomes larger, then we are encompassing these two things, and completely the valley bottom has been incorporated when this TPI is less than 0. So that is why it is said that the TPI is naturally very scale dependent. Scale is determined because it is looking the neighborhood values which are used in the analysis. TPI values reflects the difference between the elevation in a particular cell and the average elevation of cells surrounds that particular cell. And neighborhood basically defines that what cells are to be considered around that cell. So this a user can choose that while calculating the TPI, how big the search area should be. And this is the example that when we change the search area or neighborhood in terms of here in this one is in terms of scale, and then what happens. So if the search is done based on the 500 meter in this particular example, neighborhood TPI, this is how a shaded relief model or a terrain will look like this. And whereas if the search area has increased 4 times, that means it becomes now 2000 meters, then the neighborhood or this TPI values will look like this, or terrain will look like this. And here this is the shaded relief model which is a input one here, basically a digital elevation model, but shown here as a shaded relief model. And these TPI values have completely changed. So if we see the legend here, that the TPI when we are having a scale or the search area 500 meter, then TPI values are not going much lower as compared to when we are keeping 2000 meter as a search area, and TPI values are going much lower and much higher as, so significantly lower here, significantly higher, significantly not that lower relatively, and relatively not that higher here, not that lower here. So also it depends on what the search area, but generally a optimum value has to be found out, and accordingly the search area should be chosen here. So TPI values can easily be classified into slope position classes based on how extreme they are and by the slope at each point. The 2 examples here given for a larger area where different types of landforms are present, but different when we go for a small neighborhood and slope position classification is performed, then only when a small neighborhood, that means this is showing the length of a search area, and then this area is defined as lower slope, ridge, middle slope, flat and valley. However, when we go for large neighborhood, when our search area increases, then the same lower slope is defined here as a ridge. The ridge here is defined as a valley, and it is defined the middle slope, remained middle slope, this flat slope which was earlier determined based on the small search area is now have become ridge, valleys of course here remained valley. So that is why the TPI values can easily be classified into slope position classes based on how extreme they are and by the slope of each point. So this search area influences the determination of our different kinds of landforms. Here also one example is given here, that when slope positions are in this example is 500 meter search area, in this one is the 2000 meter search area. Now here like lower values where very small part of this terrain had been classified, lower value when this is the TPI is just -1 standard deviation, whereas here large area has been classified as valleys. So as we change from this thing, that means the search area, these things will change. So these are the maps are there, and that means the digital elevation model is being represented at shaded relief model, and this is the slope map derived from digital elevation model. So depending on basically that is why we mentioned as a scale dependent. So as we increase the search area, the same the landform may be classified into different categories. But basically it will depend on how rugged the terrain is. If terrain is not highly rugged, undulated like Himalayan terrain, which is highly rugged, then these classification really will change quickly if you change the search area or scale in that case. But if it is a smoothly undulating terrain, then probably while changing from say 500 meter to 2000 meter, the classification of landforms or the area, study area will not change that significantly. So this basically depends on the, of course, the terrain ruggedness, how it is rugged. So by landform categories we can classify, for which we requires 2 TPI grids at different scales. For example, as we have been taking the example, when we are having a 500 meter and 2000 meter search area. So the combination of these TPI values from different scales will suggest various landform types. As example here, that the landform classification using large and small neighborhood TPI. So when we combined at different scales together, then this is the situation that this we say it is a upland drainage. It means higher ground drainage is there. In a hilly region, it is a very common thing. And here is a hill in the valley, means in a valley area there is a hillock is there, and open slopes are there, flat hilltop there, and deeply inside streams is the example. So it depends on again TPI. Here the small neighborhood TPI in this example is very low, and this large neighborhood TPI is very high, and that way it is classifying upland. So classifying by landform category can give us much better results, because we are involving 2 TPIs which have been calculated based on 2 different scales. In this example 500 scale and 2000 scale. And an example here also, that a high TPI value in a small neighborhood combined with a low TPI, as we have seen in the previous schematic, with low TPI value in a large neighborhood would be classified as a local ridge or a hill in the larger valleys areas, as we have seen here, like in this example, but where we are having a small neighborhood TPI is very low and large neighborhoods TPI is very high. Similarly, a low small neighborhood TPI plus a high large neighborhood TPI would be classified as an upland drainage or depression, as we can see here that upland drainage and upland drainage in this example here. So likewise, we can classify the landforms based on the TPI and involving 2 TPIs of 2 different scales. Here, if another way of representing how things will be classified based on different TPIs. So for example, if we go on the right side, this is positive large neighborhood TPI. When the search area is large, the scale is large, and the TPI value is positive, then a slope will be gentle, will be classified as gentle sloped hills or tops of mesa. Mesa is a landform, or a gentle sloped hills. However, if we go for a negative large neighborhood TPI, that when we values are on the same large scale but values are negative, then we will have a U-shaped canyons or valley bottom. So just opposite landforms will be classified. Similarly, for other 2 directions, that when we go towards top or north, that positive is small neighborhood TPI, then we will classify as small hills, ridges, either mid top or the plains. Opposite to this, that the negative small neighborhood TPI is mid slope drainage or shallow type. And if we take the example here in the middle at that in this 45-degree angle, then upland drainages or depressions, here is the mid slope, small hills or ridges. So likewise, based on the TPI values, based on the scales or combining both, we can classify our landforms. And here is the final examples that here that TPI is 500 meter calculated, and here it is 2000 meter TPI. So, different based on the slope we can classify and different landform categories as here shown, the open slopes, upper slopes, mesa, and local ridges, hills or in valleys, mid slope ridges and mountain tops. And what basically what we are getting here is that based on a simple digital elevation model and TPI calculations, we can bring landform classification very accurately rather than based on visual interpretations, and maybe that may be due to human biasness. So, that may be avoided if we involve the digital basis, that is the digital elevation models and calculating TPIs, maybe first at 2 different scales and then combining and classifying that based on the landform categories. So, we can get a final product something like this. So, this brings to the end of this presentation. Thank you very much.